Hello, this is NOBsLABO, the phone operator at NOBsLABO. In the first video on the violation of Bell's inequality posted on YouTube, we looked at the phenomenon of quantum entanglement of photon polarization. In quantum entanglement of photon polarization, the polarization angle in three-dimensional space is equal to the angle in the quantum state space, so it is easy to understand intuitively, and the probability calculations are simple. In this video, we will explain the quantum entanglement of electron spin, which has a more complicated correspondence with quantum state space than photon polarization, by comparing the phenomenon with photon polarization in a way that allows for a precise understanding. As a note, there is one thing you need to be careful about. The behavior of electrons animated in this video is modeled after the Stern-Gerlach experiment of 1922, which is believed to be the first observation of electron spin. Though no actual electron spin quantum entanglement experiments have been performed that are the same as this one. Please understand that I have used the Stern-Gerlach experiment as an example to make it easier to understand what is going on. Now we're ready to go. Let's get started. Part 1. Electron spin. In the case of photon polarization, the degree of freedom of polarization is only two-dimensional, but in the case of electrons, they can also be stationary, so their spin has 3 degrees of freedom in direction. However, in experiments to evaluate Bell's inequality, electrons are emitted in one direction, just as with photons, so the degrees of freedom that can be controlled are limited to 2 dimensions. In the case of electrons, the z-axis is conventionally taken as up and down, and the x-axis as left and right. Also, unlike the polarization of photons, spin has a direction. These are called spin up and spin down, and are represented by arrows above and below. This is a pseudo-animation showing how electron spins align in one direction when a non-uniform magnetic field is applied. Similar to unpolarized photons, we assume that electrons with no fixed spin direction are emitted from the source. When a strong magnetic field is applied to the emitted electrons in the z-axis direction, the direction of their spin collapses and they become up or down spins in the z-axis direction. Once the direction of the electron's spin is determined, the direction it faces becomes the north pole of a magnet, and the opposite direction becomes the south pole. Due to the shape of a magnet, the magnetic field of a magnet has a non-uniform distribution, with the density being higher on the south pole side and lower on the north pole side. As a result, when electrons pass through a magnet, they receive a force in the direction of the spin of the electrons that are magnetically charged to the north pole, causing them to change their orbit. In electron spin experiments, this change in orbit is used to determine whether the spin of a passing electron has become up or down. Let's compare this with the photon polarization experiment. In a photon polarization experiment, 50% of the input unpolarized photons passed through the polarizing filter and 50% were blocked. This means that the polarization direction of the photon has a 50% chance of being in the same direction as the polarizing filter, and a 50% chance of being perpendicular to it. Unlike the case of photons, the direction of the spin axis of an electron is 100% likely to be the same as that of a magnet. However, the spin orientation has a 50% chance of being up or down. Similar to rotating a polarizing filter, the electron spin behaves isotropically with respect to the rotation of a magnet. The difference between the polarization of a photon and the spin of an electron can be easily understood by comparing the definition of the quantum state vector. In the case of photon polarization, we usually define the vector 1, 0 as the basis vector representing the horizontal direction and the vector 0, 1 as the basis vector representing the vertical direction. The state vector of a photon polarization in a superposition state is represented by alpha times vector 1, 0 plus beta times vector 0, 1. When a photon's polarization is collapsed by a polarizing filter, the probability of it being horizontally polarized is alpha squared, and the probability of it being vertically polarized is beta squared. In contrast, for electron spin, when a magnetic field along the z-axis causes the spin to collapse, the spin always points along the z-axis. The state vector of an electron spin along the z-axis in a superposition state is represented by alpha times vector 1, 0 plus beta times vector 0, 1. There is a probability of alpha squared that the spin will be up and a probability of beta squared that the spin will be down. Also, if a magnetic field is applied along the x-axis, the state vector of an electron spin in a superposition state is represented by alpha times vector 1 over square root 2, 1 over square root 2, plus beta times vector minus 1 over square root 2, 1 over square root 2. In the case of electron spin, the point that it differs from photon polarization is that it behaves stochastically not in the horizontal or vertical axis direction, but in the up and down direction of the spin. Also, although I won't explain it this time, there is another y-axis direction for the spin. To express this basis vectors, we need to use an imaginary axis denoted by a lowercase I. In fact, the two coefficients alpha and beta of the state vector are complex numbers, each with an imaginary axis, and each variable of the state vector can also be a complex number. I'm not going to go into this subject of complex spaces any further in this video. Now, in the case of photon polarization, the state vector rotated by theta from the vertical in real space can be expressed by the same form of vector composition formula. Since beta is equal to cosine theta, the probability that a photon rotated by theta will pass through a vertical polarization filter can be simply calculated by squaring cosine theta as cosine squared theta. This is because the angles in the state space happen to match the angles in the actual 3D space, so the calculation was simple. This illustrates the change in basis vectors when a polarizing filter is rotated in 3D space. And rotating the filter by 45 degrees also rotates them by 45 degrees. If you display the 3D space and state space at the same time, you will get an animation like this. When the filter is rotated, the basis vectors in the state space are rotated by the same angle. And an unpolarized photon has a 50% chance of collapsing into one of the two basis vectors. In the case of electron spin, just as in the case of photon polarization, changing the angle of the magnet alters the direction of both basis vectors. The two basis vectors that are orthogonal in the state space represent the up and down directions respectively. And for intermediate angles, it is necessary to find the expression of the basis vector. The basis vectors are the two eigenvectors of the state space operator matrix. On the right side, the operator matrices of the z-axis spin basis vector and the x-axis spin basis vector are shown. These are called Pauli matrices. The operator matrix for an axis tilted by an angle theta from the z-axis to the x-axis can be calculated using the following formula. The two eigenvalues of this new operator matrix can be found using the process shown in this slide. The eigenvector corresponding to the eigenvalue 1 represents the spin-up state, and the eigenvector corresponding to the eigenvalue -1 represents the spin-down state. The spin-up eigenvector can be calculated as vector cosine theta over 2 sine theta over 2, and the spin-down eigenvector can be calculated as vector negative sine theta over 2 cosine theta over 2. The wave function of the electron spin tilted by an angle theta from the z-axis to the x-axis is shown in the slide. Let's try to show this with an animation of the state space. The two basis vectors must be orthogonal, so the angle between the spin-up vector and the spin-down vector is always 90 degrees, not 180 degrees. We can also see that the angular difference between the z-axis spin-up vector and the x-axis spin-up vector in state space is only 45 degrees. In the case of polarized photons, the probability of passing is the cosine squared of the angle difference theta. On the other hand, in the case of electron spin, the probability that the spin will be in an up direction is the cosine squared of 1/2 of the angular difference theta. In other words, if the angle difference between the magnets is doubled compared to the polarizing filter, the probability of passing and the probability of spin-up will behave similarly. So let's actually animate the behavior of the electron. First, try setting the first and second magnets in the same direction and orientation. When an electron passes through a non-uniform magnetic field created by a magnet, its orbit changes direction depending on whether its spin is now pointing up or down. This is because the up spin direction becomes the north pole of the electron, and the opposite direction becomes the south pole. In this experiment, a second magnet is set in the direction in which the spin-up electrons fly. The electrons that spin down in the first magnet bend downwards and cannot pass through the second magnet. In this setting, there is no angular difference between the direction of the first magnet and the direction of the second magnet, so the electron's spin remains at 100% as it passes through the second magnet. This animation shows that when the angle difference is 0 degrees on this graph, 100% of the spin-up electrons pass through with their spins unchanged. In the next example, the second magnet is rotated 180 degrees. In this case, the direction of the magnet's axis does not change, so the direction and orientation of the electron's spin do not change either. However, in this case, the orientation of the magnet has changed by 180 degrees, so the direction of the basis vectors corresponding to the magnet has also changed by 90 degrees, 1/2 of 180 degrees. And the up and down basis vectors have been swapped. Therefore, from the perspective of the magnet, the spin of the electron that passed through the second magnet is seen to have changed to down. This means that when the angle difference in this graph is 180 degrees, the spin-up electron becomes 0% up in the second magnet, i.e., it changes to spin down. Next, rotate the second magnet by 90 degrees. In this case, the electron that passed through the first magnet has no tilt relative to the horizontal direction. So there is an equal probability that it will change its spin direction to the left or right. That is, the axis of spin will change along the x-axis. But there is a 50% chance that it will have an up or down orientation. This corresponds to the fact that if the angle difference is 90 degrees in this graph, 50% of the spin-up electron's input will be up and 50% will be down. In this video, the second magnet is oriented at 45 degrees. The electrons' input to the second magnet have an up direction in the z-axis direction. So there is a 75% probability that the electrons will spin up in the 45 degrees direction in terms of angle ratio. However, when an experiment is actually performed, there is an 85% probability of spin up, just as in the case of photon polarization. This is because, in the case of electron spin, the probability of collapse is not proportional but takes the form of a cosine squared. As shown above, in the case of electron spin, we can see that the probability that the electron will pass through the second magnet while maintaining its spin-up is calculated by cosine squared of half the angular difference between the first and second magnets. Part 2. Quantum entanglement of electron spins. This is an animation that explains the behavior of photons using the strong Copenhagen interpretation in the case of quantum entanglement of photon polarization, which I explained in a previous video. When a photon on side A passes through a polarizing filter and its polarization direction collapses, the photon on side B, which is in a quantum entangled state, also instantly collapses to the same polarization direction and passes through the polarizing filter on side B. Also, if a photon is blocked on side A, the polarization direction of the photon on side B will collapse in a direction perpendicular to the direction of the filter on side A. The behavior of electron spin is similar, but there is one big difference. The point is that when an electron on side A collapses to spin up, the electron on side B, which is in a quantum entangled state, collapses to spin down. Conversely, if side A is spinning down, side B will be spinning up. At this time, the direction of the axis along which the spin collapses is always the same on both sides A and B. However, on side A, the orbit of the electron changes up or down due to the interaction with the first magnet, but this change is not transmitted to the electron on side B. As with the case of photon polarization, this animation is a direct representation of the Copenhagen interpretation, and it is not possible to visually confirm this contraction. Next, try changing the angle between the magnets on side A and side B to 45 degrees. In this case, in terms of the angle ratio, if the electron on side A is spin up, the electron on side B should have a 25% chance of spin up. But in reality, the probability of spinning up is 15%, just as in the case of photon polarization. The results of this experiment confirm the validity of the strong Copenhagen interpretation expressed in this animation. Spooky action at a distance is not only a phenomenon of photon polarization, but also exists for the spin of electrons. Part 3. Evaluation by Bell's inequality. In this chapter, we will use desk calculations to determine how the quantum entanglement of electron spin violates Bell's inequality. The original Bell's inequality, published in 1964, was devised by John Stuart Bell to prove that quantum behavior can be described by classical physics. The CHSH inequality is also an inequality used in experiments that proved that quantum behavior goes beyond the scope of classical physics. The Wigner-d'Espagnat inequality is the simplest inequality that expresses the core of these two inequalities in terms of probability, and is often used to explain the principles of quantum entanglement. This time, we will theoretically evaluate these three inequalities based on a quantum mechanical formula, bracket notation, a formulation of quantum mechanics in the Heisenberg picture. The original Bell inequality and CHSH inequality use event correlations for each term. This correlation can be calculated using 4 probability terms, as shown in this slide. In what follows, we theoretically derive expressions for these probabilities for the case of electron spin. Let event alpha be the A side spinning up and alpha bar be the A side spinning down. Furthermore, beta and beta bar represent the state of side B. Also, the angle of the magnet on side A from the z-axis is theta, and the angle of the magnet on side B from the z-axis is phi. When a pair of electrons in a quantum entangled state is emitted to side A and side B and passed through each magnet, the probability P, alpha intersection beta, is the probability that one electron's spin will be up on side A, and the other electron's spin will be up on side B. Also, events with a bar indicate that the spin is down. This slide explains how to calculate the probability. In the case of photon polarization, the actual three-dimensional space and the quantum state space happen to correspond, so it was possible to explain it graphically. But in the case of electron spin, it is easier to understand using a concrete calculation formula. That's why I decided to explain this formula. First, we will introduce a formula for expressing the spin of an electron in a quantum entangled state using a state vector. At the top, we show a formula for expressing a linearly polarized photon as a quantum superposition of two basis vectors, horizontal and vertical. Alpha and beta represent the coefficients of superposition, and alpha squared and beta squared represent the probability of collapsing to the respective basis vectors. The formula in the next row expresses that the photon pair in the quantum entangled state is a quantum superposition state of the basis vectors, represented by ket H, which represents a state in which both are collapsed to horizontal polarization, and ket V, which represents both are vertically polarized. In this case, the photon pair will both be horizontally polarized with a 50% chance, and will be vertically polarized with a 50% chance. When electron spins become quantum entangled, they always collapse so that the spins point in opposite directions, so the state vector of an electron is expressed as a quantum superposition of basis vectors that combine opposite basis vectors, such as ket up, ket down, and ket down, ket up. If we express this equation in the form of a tensor product for later calculations, we get the last equation. As shown on the previous page, the above equation is for the state vector when electron spin is in a quantum entangled state. The basis vectors corresponding to the angle theta have already been found. The vector for spin up is vector cosine theta over 2, sine theta over 2, and that for spin down is vector minus sine theta over 2, cosine theta over 2. According to the formula of quantum mechanics, the probability on the left side is given by the square of the product of the vector of the observation by the magnet and the state vector of the quantum entangled state. In tensor calculus, when quantities have degenerated and become scalars, the tensor product becomes ordinary multiplication, so we obtain the formula for calculating the probability on the left-hand side. As a result, the probability of alpha intersection beta can be calculated as 1 minus cosine phi minus theta over 4 using the formula shown here. The probability of alpha intersection beta bar can also be calculated using the formula shown here. The probabilities of alpha bar intersection beta and alpha bar intersection beta bar show only the results. If we calculate the correlation between alpha and beta from the 4 probability formulas we have obtained, we get the familiar cosine formula. Using these equations, any of the 3 Bell's inequalities can be theoretically evaluated. One thing to note is that when evaluating actual experimental results, there are other important factors that must be taken into account, such as the resistance to errors that occur other than the theoretical values and whether or not there are loopholes in the measurement environment. Therefore, it is not possible to judge the relative merits of the 3 inequalities based solely on the results of this evaluation. The magnet angles will be set to 2 types on side A and 2 types on side B according to the CHSH inequality. For other Bell inequalities, we will pick out 3 angles from these 4 and use them. First, for comparison, we present the photon polarization results. This time, we are not showing the formula for photons. As introduced in the previous video, it is possible to easily calculate each probability term by replacing the filter failure with the filter pass rotated by an additional 90 degrees. In the case of photon polarization, the violation of the CHSH inequality can be confirmed by using filter angles of 0 degrees and 45 degrees on side A, and filter angles of 22.5 degrees and 67.5 degrees on side B. Now, the animation shows how to switch between 2 angles of the polarizing filter separately for sides A and B. The original Bell's inequality and the Wigner-d'Espagnat inequality can be violated in the same way. The animation shows how to choose 2 of the 3 angles and set them separately for the A and B polarizing filters. Using these 4 angles, we calculate the probability terms and correlation terms for the polarization of the photon and show them in this table. If we evaluate the 3 Bell's inequalities from these calculations, we get the following results. It turns out that the CHSH inequality, the original Bell's inequality, and the Wigner-d'Espagnat inequality are all violated. In the case of electron spin, the set magnet angles are 0 degrees and 90 degrees on side A, and 225 degrees and 315 degrees on side B. As already explained, with electron spin, the probability is the same at twice the angle compared to photon polarization. But the spin direction is also opposite on sides A and B, so the set angle on side B is double this and then added with 180 degrees. In fact, the only difference between the settings in the 2 experiments is the difference in these angles. This table shows the calculation results for each term in the case of electron spin. In fact, in this setting, the values of all probability and correlation terms are identical to those in the photon polarization experiment. This allows us to break the CHSH inequality, the original Bell's inequality, and the Wigner-d'Espagnat inequality in the same way as for photons. By choosing the angles appropriately, we can theoretically completely violate the three Bell's inequalities for both the polarization of photons and the spin of electrons. Now let's look again at the table showing the results of the probability and correlation calculations. You may have noticed that all of the probabilities shown in this table are actually either half of approximately 85% or half of approximately 15%. In the cosine squared function, these are the values that deviate most from linear values. By adjusting all the angle differences to that, we can maximize the violation of the inequality. This condition is called the Cyrilson limit. Now, as an experiment, let us consider swapping alpha 0 and alpha 1 on side A. As shown in the table below, in this case only the CHSH inequality is not violated. To see why, let's go back to the first table. When calculating correlation from probability, the middle two of the four probability terms in the table are subtracted, so a minus sign is added. Thus, of the four correlations, only the correlation between alpha 0 and beta 1 is negative. Switching the angles alpha 0 and alpha 1 causes the correlation terms to switch signs, and the positive and negative terms cancel each other out, causing the four correlation terms in the CHSH inequality to sum to 0. In this way, depending on the angle chosen, it is possible that other Bell's inequalities are violated but the CHSH inequality is not. Of course, there are conditions under which the original Bell's inequality or the Wigner-d'Espagnat inequality is not violated depending on the choice of angle. However, it should be noted that the CHSH inequality does not always produce the best results. Also, as you can see from doing calculations like this, knowing the individual probability values when calculating correlation makes it easier to understand the relationships between the various Bell's inequalities. This concludes this article. What do you think? As far as I have researched, it seems that in the case of electron spin, a complete experiment that eliminates loopholes like the photon polarization experiment has not yet been performed. Photon polarization and electron spin seem to be completely different phenomena. Nevertheless, the existence of quantum entanglement, which gives exactly the same probability and correlation results for both, seems so miraculous. The moment a polarizing filter or magnetic field is set to a certain angle on one side, the quantum angle of the other pair, which is far away, definitely collapses to the same content. Moreover, this miracle is realized without violating the theory of relativity. However, if you look at it from a different perspective, it is not that anything is possible, that is, it is not that everything in this world does not exist, but that it certainly moves according to certain laws. Otherwise, such a coincidence would not be possible. God rolls the dice, but it is not just any dice. Goodbye now, from NOBsLABO.